Lecture 6.5, thin lenses and the thin lens and magnification equations. So what we're doing here now is that we are now looking at the mathematical description of images. So just to make sure that we're off to a good start, let's look at these notations that we're looking at. So S is the object location. S prime is the image location. And F is the focal length. So there's three others. There's M, which is the magnification. There's the height of the object, which is the object height. And finally, we're left with the image height. So if I write H, sometimes it's the height of the object. If I write H prime, it's the height of the image. So this is the image height. So that's our notation. There are three equations. So the first one we just covered. This is the lens maker equation. And we saw that the lens maker equation determines the focal length. Right, in this equation, we saw that 1 over f is equal to the index of the lens times the product, the sums, or the differences of two radii of curvature. Now what we're going to be looking at is we're going to be looking at the thin lens equation, and this reads 1 over f, which is 1 over s plus 1 over s prime. And then finally, we have our third equation, which is the magnification equation. And the magnification equation reads m, which is minus s prime over s, where its magnitude is the height of the image divided by the height of the object. So these three equations give us the mathematical description of these guys. So now, let's look at these. So I'm going to focus on the thin lens equation and the magnification equations. These equations are not difficult to solve for, but you got to be careful of the signs because it's easy to get the signs incorrect. So here we go. So what I'm going to do here is I don't want to try to make a big deal here about the signs here. So let's look at the sign convention. For all of them. So here we go. So if I have a lens, Remember, so what we're going to be doing here is that we're going to be looking at small lenses here. So I'm going to actually reduce this in size. Okay, so here's going to be my. So if I look at this guy, what is it that I'm actually seeing here? For starters here, I'm going to look at the focal length. So here's my central axis. And what I'm going to do here is that I'm going to copy this because I'm going to use this again. So now what I'm going to focus on is I'm going to focus on the focal length. So the first one that I'm going to look at is I'm going to look at the focal length. We've already done this, but let's just be careful with the sign conventions. So if I'm on the right side here, right? So if I'm on this side over here, this tells us that the focal length is positive. And this can only be for a converging lens. On the other hand, if I'm on this side, then this guy has a negative focal length, and this can only be true for a diverging lens. In other words, when I look at my sign convention, I have two possibilities. I have positive, excuse me, I have a positive and a negative sign, and that tells me that this is converging, and this tells me that this is diverging. Now let's look at the object. So now I'm going to look at the object location. So if I look at the object location, I'm going to do the exact same thing. I'm going to put this right here, and what I'm going to read here is that now I'm going to see something like this here. So if I'm on this side right here, we expect light to go through the lens because it's coming from the left towards the right here. So in this case, this object is a positive value, and this is a real object. And that means because the object is on the left side of the lens. Now, there is a second situation. And this only occurs for a two-lens system. I can have an object that's negative. This is called a virtual object. So then if I look at my sign convention for this guy here, if I see a positive sign, this means I have a real object on the left side of the lens. However, in a two-lens system, I can have a virtual object that's on the right side of the lens. But remember what I just stated here. This only occurs for a two-lens system. By the way, it can also occur for a lens mirror system. And then finally, we have our image location. So if I look at my image location, it's the same as before here. But think about it in a more physical way here. If I have an object on the left, we expect the light to go through the lens. So if I look at this guy, then what I'm going to see here is that on this side here, because we're talking about an image, we're going to say that an image should be positive on the right because we expect the light to go that way, right? Remember, the light is going this way. So we're expecting the image to form on the right. Because of this, we call this a real image. That means we can take a screen and capture that. On the other hand, if it's on this side, the left side, it's kind of odd that there's an image that's formed here because we expect the light to go through the glass. So now, in this case, that image is negative. And this is what we call a virtual image. So when I look at that sign, excuse me, the sign convention, if I have a positive, it's a real image formed on the right side of the lens. On the other hand, if I have a virtual, I have a negative, and that's formed on the left side of the lens. So that's our sign convention for these locations of the focal length object and image locations. Now, the last thing that we want to look at is we want to look at the magnification. So what we're finding here is that we have this thing called M. So M, by definition, is called the lateral magnification. Now, I dropped the word lateral and I only call it the magnification because that's the only magnification that we deal with. And so there's two pieces of this thing. So now let's look at the magnification. So the magnification, what does it mean if it's positive or negative here? Okay, so I'm gonna write this. I'm not really sure how to do this. So let's set up our coordinate system again. So here's what we know: is we have two sides. So if I look at this side over here, and I'm looking at an image, we know that images on this side here are going to be real images. On the other hand, on this side over here, we know that these images are virtual images. So now let's look at the magnification here. So if I look at the magnification, it reads minus S prime over S. So what does this mean here? And what you want to focus on is that you want to focus here, so you want to focus on the sign of S prime. Okay, the sign of S prime. Now, S for a single lens is always positive. So it's the S prime that's going to tell you. So what you're seeing here is that if I have a positive sign. The only way I get a positive sign if S prime is negative. So this implies that a positive value means S prime is negative. So therefore, if the image is negative, that means that the image must be virtual and an erect image. In other words, in this location here, that magnification is positive. So I have a positive magnification here. On the other hand, if I have a negative sign, that means that a negative value means S prime is positive. So therefore, this tells me here is that if my magnification is negative, I'm going to have real inverted images. So then this is, of course, negative magnification. So you gotta pay attention to that sign, because this is the one that really messes a lot of people up here. So then the last thing that we want to look at here is that the lateral, that the magnitude of the magnification determines the size of the image. So then the magnitude of the magnification, that this guy is equal to the image height divided by the object height. And again, we've said this before here, but this tells us that if the magnification is less than 1, then that tells us that it's smaller. If the magnification is equal to 1, then it's the same size. And finally, if the magnification is greater than 1, then the image is larger than the object. Now, to give you a sense of where we're at on this thing, let's look at this thing a little bit differently. So let me put out a ray diagram. And so what I want to do here is that, let me move this down a little bit. Maybe I'm going to write a little bit first, is that I want to interpret the magnification by ray diagrams. So the key point here is you got to look at really the sizes of the image distance versus the object distance. So the key here, or the key point, is to compare the lengths of S prime versus S, because it tells us that if I look at the magnification, it's really, where these are now absolute value, I am comparing these two distances. So let's let's look at just a converging lens. I could do this for a diverging lens, by the way, very easily. So what I'm going to do here is that I'm going to pick these are my focal points and my two F points. And for the sake of simplicity here, I'm going to call this positive. You know what? I think I'm going to have to make this a little bit longer because I'm going to run into trouble. So I'm going to come up here. And I think I'm just going to keep it like this. So now what I'm going to do here is that I'm going to copy this. And let's just start drawing this guy. I'm going to separate these guys into 4 so that we can look at these guys. Okay, so here we go. So for the sake of simplicity, all of these are going to be positive focal lengths. So now I'm going to pick my object. Okay. So my object here is going to be outside of 2F. So what I want you to see here is that note that this guy is large because it's outside of 2F. So now let's go do the ray diagram. So if I choose my ray diagram, you could see here is that I'm going to pick this guy right here. Then I'm going to go through the focal length. Then I'm going to get my second one, and my second one looks like this. And you could see here is that my image is right here. Now, the first thing that I want you to pay attention is look at the distance here. What you're seeing in this situation here is that S is greater than S prime. So that tells me immediately that the magnification has to be smaller. Now let's keep changing this. Now what I'm going to try to do here is that look at the distance here. So here's my object. And so this distance is S again. So let's try to look at this guy again now. So if I draw my ray diagram here, that's not the way it should go. Then here's my second ray. You could see here is that this ray, where they cross, you could see that this distance, S prime, that these two guys are the exact same length. So in this case, because these guys are the same, that then this tells us that the magnification is 1, so therefore they're the same size. So by looking at the value of S and S prime, it tells you that. Now let's do the exact same thing. But in this case here, we're now going to put our object in between F and 2F. So again, what you're seeing here is that here's my S. So now, doing the same thing as before, I'm now going to do this. And if I now look at my image, it's right here. And if you look at this distance here, this distance is larger because S prime is larger than S, that tells us that the magnification is greater than 1, so it's larger. Again, I'm comparing those two distances. Excuse me, the same thing happens even if I have a virtual image. So look what happens. Here's my object right here. And you could see that that distance is going to be really tiny right here. That's going to be my object. So now let's go look at our ray diagram. So if I look at my ray diagram, then I got to follow it back. Right, it goes like this, then I follow it back. Now looking at my second ray, and you could see that the image distance is still larger than the object distance. It's still farther from the lens. So therefore, S prime is greater than S. So that tells me then that the magnification is greater than 1. And therefore, I get a larger image. Now let's go look at example 6.2, where we go through multiple problems.